So signal strength. Signal strength. What is signal strength? Signal strength means that how close it approximates the ideal voltages, and by ideal voltages we mean the logic thresholds that we defined previously: VIL, VIH, VOL, VOH, VOL. Okay, so how close is your signal to these voltage ranges? VDD and ground are called rails. Okay, and they are the strongest ones and they are the strongest zeros. Okay, so other signals in your circuit, they may be weak. I mean, they may not, the one may not be represented with 5 volts. It may be represented with 3.8 volts. So that is a weak one. But the VCC and or VDD and ground, they are the strongest in terms of the voltage rails that they gave. So NMOS passes strong 1. This is important to note. Strong 0. So NMOS can pass a strong 0, but a weak 1. What is the reason for this? We will discuss this when we go into the structure of NMOS in the later lectures. But you have to remember this for this time being, that NMOS can pass a strong 0 but a weak 1. PMOS is opposite. It can pass a strong 1 but a weak 0. And that is the reason, if you remember, that the pull-up network, it used PMOS. Why? The reason is it passes strong 1, and the pull down network, it uses NMOS. What is the reason? The reason is it passes strong 0. Okay, so this is something that is important, and that tells us the reason why the pull down network is PMOS and the the pull up network is PMOS and the pull down network is NMOS. Okay, now let's come to pass transistors. So basically pass transistors are single transistors. For example, it can be a PMOS or NMOS. So they are used when they are used separately. Okay, so that are called pass transistors. So for example, this is a NMOS pass transistor. This is NMOS pass transistor. This is a PMOS pass transistor. And what is the advantage of using them? They can be used as switches, and for example, when the gate is 0 for PMOS, it is open. When the gate is 1, it is closed. So when it is closed, what is passed? Whatever is at the input. So if at the input we have logic 0, the output will be a strong 0. And if it is a logic 1, it will be a degraded one, because this is NMOS. Similarly, for PMOS, if the gate is 0, it is closed. So you see, these both cases are for closed. So when this is 0, what happens? And when this is 1, what happens? When 0, a degraded 0 is passed because it is a PMOS, and when the input is 1, a strong 1 is passed. So transistor, transmission gates. So transmission gates are basically composed of pass transistors, and they have this ability that they can pass both 0 and 1 well. Okay, so here is a pass transistor. Okay, sorry, a transmission gate. It has two pass transistors. This one, which is NMOS, and this one, which is a PMOS, and they are connected in this parallel fashion. So for example, there are two control signals, G and GB. When G is 0 and GB is 1, for example, for this case, so what happens when this G is 0? This NMOS is open, and when GB is 1, the PMOS is also open. So there is no path between A and B. Okay, what happens when G is 1 and GB is 0? When G is 1, the NMOS is closed. So we have one path for A, from A to B. So in that case, what happens is we apply 0, okay, it will pass a strong 0, and when we apply a 1, it will pass a strong 1. Okay, so this is in contrast to so you may ask that why the transmission gate can give us a strong 0 and a strong 1. Remember, the case was different for a pass transistor. A pass transistor can, if it is an NMOS, it gives you if it is an NMOS, it gives you a strong 0. If it is a PMOS, if it gives you strong 1. So what is different here? That it can give you both a strong 0 and a strong 1. For this you have to look to where the inputs are connected. So the G and G bar, okay, they are control signals. They are not your inputs, they are control signals. And basically G bar is this one, it's not of G. So what are the input? The input is this one and this one. Okay, so depends on how you want. You can transfer A to B, or you can transfer B to A. So that's why that when A and B are connected, controlled by the switch G and G bar, so the A and B are strong, they are already strong. If the A is 0, it is strongly connected to B. If the A is 1, it is strongly connected to B because there is no degradation across the transistor. Okay, in separate NMOS or PMOS, the scenario was like this. So from here you are taking, for example, your V out, and this was your gate, and this gate was your input. So when the gate was, for example, 0, it was closed and you get a strong 0. But when it was 1 and the gate is closed, you get VCC connected to the output. But as I told you before, due to the internal structure of NMOS, there are some resistors that come in the effects, and at the output we get a voltage that is less than VCC or VDD. Okay, so that's why we said that the NMOS passes a strong 0 but a weak 1. And in this case, in the case of pass transistor, this cannot happen because there is no degradation across the transistor. We just connect two signals together. They are just two wires connected together. So whatever is the strength here, the strength is transferred to the other side. So that's why the pass transistors, transmission gates are good, and they passes strong 0 and strong 1. Now we come to the other combinational, you can say, gate, which is called tri-state buffer. So what is a tri-state buffer? A tri-state buffer is like a buffer, but it has a control input, that is enable. So when the enable is 0, okay, when the enable is 0, for example, for this tri-state buffer, it is open. So A and Y are not connected. And when A enable is 1, A is connected to Y. So when they are not connected, we call it Z or high impedance. And when enable is, so this is for enable 0, these two entries, and these two entries for enable 1. When enable is 1, whatever is on the A, it is transferred exactly the same to B. Okay, so this is, you can say, this is called active high tri-state buffer. The opposite can be, for example, this one, which has a bubble. This is active low tri-state buffer, TB. Okay, so we can build the tri-state buffer from transmission gates, and we can use only two transistors. Okay, how? So for example, we have an NMOS and we have PMOS connected in this fashion. So when enable is 0, the above this one transistor will be on. okay, and when it is 1, this one will be on. So you can pass the signal in both cases. But this kind of transmission gate has one problem. The problem is, you remember that other gates were regenerative, they were restoring, but the transmission gates are non-restoring. It means that when the transmission gate is closed, so if there is a and this A is connected to B, okay, if there is some noise that comes and adds up with A, okay, the noise will be transferred to B, okay. Remember, it was not the case in CMOS gates. The CMOS gates could restore the logic levels. So this is one problem with transmission gates. The advantage is, what is the advantage? Transmission gates advantage, what is the advantage? Advantage is they can pass strong 0 and strong 1. What is the disadvantage? The disadvantage is they are prone to noise, okay, and non-restoring. So this is the disadvantage. Okay, so here is the tri-state buffer. This is a tri-state, basically a tri-state inverter. So you have this symbol, you have this A, you have this B, and you have this control signal. So you want this tri-state inverter circuit. And how we can build this? We can build this by composing, by combining 2 PMOS and 2 NMOS transistors. Okay. How this works? This works like, if enable is 0, okay, so this is the enable signal. It is connected here and here in inverted and non-inverted form. So when enable is 0, the NMOS is open and also the PMOS is open, okay, because that is enable bar. So when this is 0, this will be, the gate of PMOS will be 1. So for example, if you apply 1 here and 0 here, so the result will be that this will be off and this will be off, okay. In that case, what will be the output? The output will be Z, high impedance, okay. So when enable is 0, you cannot pass A to B, but when enable is 1, then the story changes. Both the internal transistors are on, okay, and what you get is this circuit. Okay, so let me explain what this circuit is. Let me redraw this. So this is our input A. From here we take our output. Here is our VDD. Here is our ground. So what is this circuit? Imagine if we apply a 0. Okay, so for a 0, this will be off. This will be on. It has a bubble, so the PMOS will be on, and this will be off, which means we will have VDD connected to Y. So if we gave it a 0, it gives us a 1. Now imagine the other case. Let me draw again. So this is our A, this is our Y, this is VDD, this is ground. Imagine we gave it 1 as an input. So now for 1, this is off and this is on. So in that case, the ground will be connected to Y. So if we gave it a 1, it gives us a 0. So this is basically a CMOS NOT gate. Okay, so that's why if enable is 1, then the whole circuit becomes an inverter, and whatever is at the input, it is passed to the output but inverted. Okay, now we come to another important circuit, that is multiplexer. So what is a multiplexer? A multiplexer can choose between two inputs. So imagine that you have one output and you want to connect it to two inputs, D0 and D1, and which one will connect depends on the signal S or select signal. Okay, so let's come to the truth table. The truth table is like this. When the select line is 0, okay, when this is 0, D0 is connected. Okay, so D0 is connected to I, in which case, in which S is equal to 0. So when D0 is connected to I, whatever is on Y, D0, it appears on Y, and the other one does not matter, it is X. When it is 1, D1 is connected to Y, and this does not matter, D0 does not matter. Okay, so this is called a 2x1 multiplexer. How can we build this 2x1 multiplexer from transistors? This is the Boolean equation of a 2x1 mux. You can derive this equation from the truth table. So it is S D1 plus S bar D0. So how many transistors are needed for this circuit? Okay, so we saw that for a NOT gate, this was the NOT gate. What was the circuit? The circuit was consisting of two transistors. Okay, so for NOT gate, the circuit consists of two transistors. What about a two input AND gate? Now remember that in CMOS logic we don't have AND gates. With what we have is we have a NAND gate and we have to put an inverter in front of it. Similarly, we don't have OR gate. What we have is a NOR gate followed by a NOT gate. Okay, so this is what you have to remember. If you remember the circuit for AND gate, it was 4 transistors, 2 transistors for NOT, 4 transistors for NOR, 2 transistors for NOT. So if you want to implement the above equation, so this is the circuit. This is the circuit with AND gates, and this is the circuit with NANDs and NOTs. So basically this is a NOT. Okay, this is a NOT, and this is a NOR. Okay, so now counting the number of gates, we have 4 plus 4, 8, 10, 12, 14, 18 and 20. So we have in total 20 gates, 20 transistors, 20 transistors for a 2x1 mux. Okay, but if we implement the same 2x1 mux with transmission gate, we only need 4 transistors. So this is the circuit for a 2x1 mux. Okay, and we have one transmission gate here, another transmission gate here, and this is a 2x1 mux. For example, let's say that S is 0, so this is 0 and S bar is 1. So what this means? This means that this transistor is on and this transistor is on. This transistor is off, and this transistor and this transistor is also off. In which case what will happen, that Y will be equal to D naught. Okay, so this is according to the mux functionality. Similarly, for S is equal to 0, we have Y is equal to D, and if you check yourself, for S is equal to 1, Y will be equal to D1. Okay, so this is a 2x1 mux. But the good thing is it only needs 4 transistors compared to 20 transistors if you do it with CMOS logic. Okay, what is the downside? The downside is, we know that the transmission gates are non-restoring, so they are vulnerable to noise. And similarly, we can develop a inverting mux. So an inverting mux uses one of the circuit, the A0112. This was discussed in the previous slide. So it uses that compound gate, or you can use a pair of inverters. So this is when you implement it with AOI22, and this is if you implement it with pair of inverters. Okay, so again you can easily check by applying the values of S1 and S0 to these circuits, and I hope that by now you can do it yourself to verify that indeed both these circuits, this 1 and 2, they both are mux. Okay, so you can develop this kind of truth table. So S, D0, D1 and Y. You can develop this truth table for both these circuits, and you will come to know that the truth table is for a 2x1 mux. On the right, this is the symbol of a multiplexer. So you see the shape, it's like a parallelogram, this side up and this side down, something like that. And because this is an inverting mux, we have this bubble here. So this is how you can design a 4x1 mux using a 2x1 mux. Let me tell you that the select line of, so for example, this is mux 1, this is mux number 2, and this is mux number 3. The select lines of mux M1 and M2, they are shorted. So in this way we have two select lines, S1 and S0, and we have 4 inputs. We have D0, D1, D2, D3. Okay, so we have these two select lines, we have 4 inputs, and we have 1 output. So we know the CMOS level circuit of a 2x1 mux, so we can draw the CMOS level circuit for a 4x1 mux by using the same circuit 3 times and interconnecting it in this fashion. Okay, if I ask you to construct a 8x1 mux, okay, you can do it again by using 2x1 mux. So an 8x1 mux has 8 inputs. So here we have 8 inputs: D0, D1, D2, D3, D4, D5, D6, D7, and this is 0, 1, 0, 1, 0, 1, 0. And on this we connect another layer of muxes. Okay, 0, 1, and on this we connect the final mux 0, 1. So this will be our most significant S3, and this is S2, and this is is not. Okay, so this is a 8 cross 1 mux, and you can scale it if you want to 16 cross 1 or something like that. Okay, before I go into the details of this one, which is D-latch, let me tell you something more about the two topics that we discussed. One was tri-state buffers, okay, and the other topic was mux. So one interesting application of the tri-state buffer was like this. In computers, you have a shared wire that is called a bus. So if you have something, for example a component here, okay, this may be a component, and this component wants to connect to the bus. It is always connected through this is tri-state buffer. So what is the advantage? The advantage is that this buffer is connected not to one component, but this is component 2. So this is component 1. This is connected to several components. So if, for example, C1 wants to use the bus, it will enable its pass transistor, and there will be a connection established between the C1 and bus, and C1 can put some value on the bus. At that moment, C2 will disable its connection. Okay, so C2 is not putting something on the mux. Okay, but if C2 is, for example, the receiver, then we will have another tri-state buffer like this on the receiver side, and this will be enabled. So C2 will enable the receiving buffer. So this is the receiving tri-state, and this is the transmitting tri-state. This is the transmitting tri-state of C1. So C1 will also have a receiving tri-state. So all these tri-state buffers are controlled, and who controls it? The control unit controls it. And so that is the story of tri-state buffers. But the mux is an interesting element. You can also use the mux for this kind of functionality. If you want to put something on the bus, you can use a mux. Okay, and because a mux can also give you, if you want to connect, for example, 10 elements, if you have two components, C1 and C2, okay, for example, and this is your connection to bus, so you can put C1 here, you can put C2 here. Okay, so instead of a tri-state buffer, you can do it like this. Okay, so in more recent times, mux are used instead of tri-state buffer, because tri-state buffer has certain disadvantages. They are more susceptible to noise and all these things. So currently most of applications they use mux. So this is it for the combinational logic and how we design the building blocks of combinational logic. So to summarize, in this part we have studied how we can design gates, for example AND gate, OR gate, NOR gate, NAND gate and NOT gate, and then we went to discuss the transmission gates, and then based on that we went to discuss tri-state buffers and muxes. So this is the combinational part of story. In the next lecture we will go to the sequential part, which will be two fundamental elements, which are D latch and flip-flop. These are the building blocks of sequential logic. So we will see how we can build those fundamental blocks from the transistors and what are different details that are involved. Okay.